तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We had considered several interesting properties of the Laplace transformation in the last two lectures. So it's a good time now to work out a number of examples which illustrate the application of these properties. First example, let us find the Laplace transform of a function f of t which is represented graphically in this form. This is t in seconds. F of t has a value of 4 units at t equals 2 seconds. So this is the function f of t whose Laplace transform we are required to find. So we can express this f of t as, from this point to this point it climbs by an amount of 4 units in 2 seconds. Therefore, the slope is 2 units. It is a ramp function. It is 0 for negative values of time. Therefore, 2 RT. This describes the behavior from 0 to 2. At this point, instead of climbing up at a rate of 2 units per second, it is climbing down at the rate of 2 units per second. 2 units per second, because in 2 seconds it comes down by 4 units. Therefore, the net slope must be minus 2. Therefore, you must bring this positive slope of 2 units to a negative slope of 2 units. Therefore, you must introduce a negative ramp of 4 units, and then that ramp is introduced at t equals 2 seconds. Therefore, this minus 4 RT minus 2. So if these two ramps alone were operating, then this continues to go down like this. But at this point, the downward slope must be arrested, a net slope of minus 2 must be arrested, and then it should be flattened out. Therefore, to introduce another slope of plus 2 units at r at t equals 4. So it is these 3 ramp functions which describe this characteristic. Therefore, we can find f of s as 2 upon s squared minus 4 upon s squared would be the Laplace transformation if it has been 4 RT, but since this is delayed by 2 units, you must introduce e to the power of minus 2s. And this has a ramp of 2 units, therefore 2 over s squared is a basic Laplace transform of the ramp function, but since it is delayed by 4 seconds, you must introduce e to the power of minus 4s. So that would be the Laplace transformation of this. It is illustrative to obtain the same result by differentiating this f of t maybe once or twice and finding out the Laplace transform of the derivative functions, and then go back and see how it agrees with this or not. So let us see. If I take the derivative of this f prime t, then for 0 to 2 seconds it has plus 2 units slope of plus 2, and from 2 to 4 seconds it is a slope of minus 2. So that would be the derivative function, 2 and minus 2. that is the derivative function, that is f prime t. Now, if I take the second derivative of this, once again take the derivative of this, you have here, we are thinking of this is 0, therefore, this is also 0. Therefore, there is an impulse of 2 units here, 0 to 2, 2 units impulse, and at this point it jumps from plus 2 to minus 2. Therefore, there is a negative impulse of 4 units, therefore, minus 4 is the strength of the impulse. At this point again it climbs up by 2 units, therefore, this will be 2. So, you can write f double prime t, that is the second derivative of the function of time f double prime t, as 2 delta t minus 4 delta t minus 2, because that is an impulse standing at t equals 2 seconds, plus another impulse function of 2 units at t equals 4. This is the second derivative of this. The second derivative now consists purely impulse function, therefore, its Laplace transform is easy to find out. So, Laplace transform of the second derivative is delta t has a Laplace transform 1, so it is 2 minus 4 delayed impulse minus e to the minus 4 e to the power of minus 2s, and this is again a delta function, therefore, this is 2, and but it is a delayed impulse, therefore, you must introduce a term e power minus 4s. So, that is the Laplace transform of the second derivative. To find the Laplace transform of the first derivative, that is, this is obtained by integrating this. So, if you know the Laplace transform of this function, the integral will have the same Laplace transform divided by s. Therefore, this will be having the Laplace transform 2 upon s minus 4 upon s e to the power of minus 2s plus 2 times e to the power of minus 4s over s. In addition, normally you have the integral value of this function at t equals 0 minus, in this case it is 0, therefore, that does not appear here. Now, once we have the Laplace transform of this, the Laplace transform of its integral, that is the Laplace transform of this, is obtained by multiplying this by 1 over s once again, and that is what you are having here. So, this also illustrates that the possibility that when you want to find Laplace transforms of functions like this, you may find them directly, but alternately you can take the derivatives and find if the derivatives Laplace transforms are easily found out, then you can use that information to find out the Laplace transform of the original function. The two alternative approaches. It also illustrates the rule for integration that we have already discussed. Let us take a second example. A. Find the Laplace transform of t cubed e to the power of minus at ut. And after having found that out, evaluate zero to infinity of t cubed e to the power of minus at dt. This is the question that is asked for us. Now, to find this out, we can, let us say, method 1. We start with Laplace transform of t. We know t ut, that is 1 over a squared. T squared ut is minus d by ds of 1 over a squared, because this is multiplied by t. Multiplication in the by t in the time domain corresponds to the negative of the derivative in the s domain. So, minus d by ds of 1 over a squared, which of course is 2 upon s cubed. Then likewise you can carry this one more step. T cubed ut will be, you once again have to take the derivative of this. This will become 3 factorial by s to the power of 4. That is t cubed ut. But now if f of t has a Laplace transform f of s, f of t multiplied by e to the power of minus at, the Laplace transform of that is obtained by substituting s plus a for s. This is something which we already discussed. Therefore, t cubed ut multiplied by e to the power of minus at, its Laplace transform is obtained by substituting s plus a for s. So, this will be 3 factorial or 6 over s plus a to the power of 4. This is, that is what it is. Now, let us do this by taking another approach, method 2. Let me start with the Laplace transform of e to the power of minus at ut. So, e to the power of minus at ut has the Laplace transform 1 over s plus a. Now, t multiplied by e to the power of minus at ut is once again minus d by ds 1 over s plus a. That will be 1 over s plus a whole square. Then likewise t squared e to the power of minus at ut, that will give me, by the same process, taking this second derivative, again the derivative of this with respect to s and putting a negative sign, it becomes 2 over s plus a whole cube. And t cubed e to the power of minus at ut will fetch me 2 times 3 factorial over s plus a to the power of 4. So, that is the same result that we obtained earlier. So, this problem we worked this out taking 2 different approaches, starting with the Laplace transform of t cubed ut first, or Laplace transform e to the power of minus at at first. As I said, these are 2 alternative ways of doing this. Now, for the second question, now let g of t be t cubed e to the power of minus at ut. It has got the Laplace transform, let us say g of s, which is this, right. Now, if I take the integral from 0 minus to t of gt dt, you can say 0 because after all there is no, the 0 plus value of g of t is also going to be 0, therefore, whether you take 0 minus or 0 plus makes no difference. So, I simply write 0 to t of gt dt. This has got the Laplace transform gs upon s, because the initial value of the integral is taken to be 0, therefore, it is gs upon s. Now, what is 0 to infinity of g of, suppose this is ht or some, what we want is not 0 to t, but 0 to infinity. Therefore, 0 to infinity of g of t dt can be regarded as the final value limit as t tending to infinity of h of t. So, the final value of this function we want to find out. This function has got this Laplace transform gs over s. To find out the final value of this function, this is equal to limit as s tends to 0 of s times g of s over s. That is the final value theorem. To find, if you know particular function has a Laplace transform gs over s or whatever it is, h of s if it is, if you like, then the final value of h of t, h infinity, is obtained by taking the limit as s goes to 0 of s times h of s. Now, in this case s times g of s over s. So, this is indeed s cancels out g of 0. So, the final value of the integral from 0 to t of gt dt, it happens to be simply g of 0, where g f s is the Laplace transform of this quantity. In our case, g f s is equal to this. Therefore, the final value, that means when s is equal to 0, this is 3 factorial is 6 upon a to the power of. So, that is the answer for the second part, 6 upon a to the power of 4. In other words, what we are having is, the principle that we are using here is, if f of t has a Laplace transform f of s, what we are saying is 0 to infinity of f of t dt is equal to f0. That is what the principle that we have used here. This is quite easy to see why it is so, because after all f of s equals 0 to infinity of f of t e to the power of minus st dt. When you substitute s equals 0 in this becomes f of 0, and this is 0 to infinity of f of t dt, because this becomes 1. When s is equal to 0, this becomes 1. And that is the same thing that we have used here. So, all these are tied up in some fashion or other, but what we wanted to do here is to illustrate the rule for integration, and then they also want to illustrate the application of the final value theorem in working out the solution. As a third example, let us consider the convolution of a function of time with a delta function or a unit step function. So, using Laplace transforms, find what these functions amount to. F of t convolved with delta t first, b f of t convolved with u of t. If you recall, the results we already know. When we talked about the convolution property in the introductory lectures, we said whenever a function is convolved with delta t, that function is reproduces itself. That means f of t star delta t is f of t itself, because the delta t scans this function as it moves along, and at any particular point the value of the product of delta t and that f of t, the displaced delta t and f of t will be f of the value of the function at that particular point of time, that is the magnitude of the impulse, and when you integrate, that will be f of tau times f of tau whatever it is, wherever it is situated. Therefore, the convolution of this will be must result in f of t itself. And when we talked about the integration rule under Fourier transforms, you recall that f of t convolved with u of t has been shown to be the integral of f of t. We will see these results here in the using Laplace transforms. So, A, we know that the Laplace transform of f of t convolved with delta t is the product of the Laplace transforms of the two individual functions. This is f of s multiplied by 1. The Laplace transform of delta t is 1, therefore, this is f of s. And the inverse Laplace transform of f of s is equal to f of t. Therefore, f of t star delta t is f of t itself. That is what we already know. Second question, f of t convolved with u of t has for its Laplace transform f of s multiplied by 1 by s. So, this is f of s over s, and we know that f of s over s has the inverse Laplace transform 0 minus to t of f of t dt. So, when you convolve f of t with a unit step function, it is the integration of f t. In the Fourier transform theory, we might have taken this from minus infinity onwards, but in the Laplace transformation, because we are dealing with causal time functions, we take the limit from 0 minus to t, because f of t is assumed to be 0 for negative values of time. That is the difference. So the integral of f of t dt from 0 to t is f of s over s, and that is indeed the product of the Laplace transforms of these two functions. Therefore, we conclude that f of t star ut is 0 to t of f u du if you wish, because after all this is a dummy variable, the integral of f of t, assuming that f of t is a causal time function, and therefore we are starting the limit integration from 0 minus onwards. These results are already known, but this is only a confirmation of results that we already derived in an earlier context. Example 4. Let us consider now a section of a circuit in which we have an inductance L of 1 Henry and a capacitor of 1 farad, and let the voltages across the two elements be described as Vc and Vl. In some circuit analysis, we have obtained Vc, the Laplace transform of Vc of t, the Laplace transform of the voltage across the capacitor is found out to be As plus B over S squared plus Cs plus t. Through some analysis, we have obtained this. Using this information, we are asked to find Vc0 plus the voltage of the capacitor immediately after 0, the current in the circuit at 0 plus, this is the current IT, and the voltage across the inductance at 0 plus. These are the three quantities that are required to be found out. Right? Now, since we are interested in finding out the 0 plus values in all these situations, we can assume that the Laplace transform that we are talking about, f of the Laplace transform defining integral, start from 0 plus 0 onwards, not from 0 minus, because we are after all interested in 0 plus values. That means we ignore any jumps in these functions from 0 minus to 0 plus. We assume that all our functions starting from 0 itself, and therefore we can use the 0 plus value instead of 0 minus value wherever it is necessary. So let us see. Vc0 plus, the initial value of the capacitor voltage, is limit as s goes to infinity of s times Vc of s. That is the initial value theorem. Therefore, this will be limit as s goes to infinity of As plus B upon say s square plus Cs plus d multiplied by s. This must be multiplied by s and take the limit as s goes to infinity. Therefore, that will be As squared plus Bs over s squared plus Cs plus d. And when you take the limit as s goes to infinity, as I mentioned in the last lecture, we can take s going to infinity in the along the real axis, in the positive time axis. Therefore, we can, this is the ratio of the two leading coefficients only, because all the other terms pale into insignificance. Cs plus d pales into insignificance with s squared. Bs becomes negligibly small compared with As squared. Therefore, it is the ratio of the two leading coefficients. Therefore, this is given. So the immediately after 0, the capacitor voltage at 0 plus, as you approach 0 from the positive direction, will have a value A. Now, what about the current? We know that the capacitance I equals C dV C dt. That is the relation between the current in a capacitor and the voltage across the capacitor for any general variables IT and Vc. Therefore, I equals C dV C dt. Therefore, we can say the Laplace transform of the current IFS is C times, if Vc has the Laplace transform Vc of s, the derivative dVc by dt is S times Vc of S minus. Now we are taking stock of all values from starting from 0 onwards, 0 plus onwards. Therefore, I may write here Vc 0 plus. If we are starting all our accounting from 0 minus, you would have put it at 0 minus. That means I am trying to take the value variation of current. Suppose this is a variation of current. I am taking the stock from 0 plus onwards only. I am not considering the jump from, if any, from here to here. Okay, right. That means if there is any jump in Vc, suppose Vc 0 minus is this and Vc 0 plus is this, the current would have an impulse here. But those impulses I am ignoring. I am talking about the variation of the current I for t greater than or equal to 0 plus. Only that is the type of current which I am interested in. So that is why I am putting Vc 0 plus. So this will be, C in our case is 1 farad. So this will be S times Vc of S. Vc of S is As squared plus As plus B over S squared plus Cs plus B. Therefore, S times Vc of S is As squared plus Bs over Cs squared plus Cs plus D minus Vc 0 plus has been just been evaluated, that is A. Therefore, when you do this, then it becomes B minus Ac times S minus Ad divided by S squared plus Cs plus D. That is the Laplace transform of the current IFS. To find out I0 plus, we apply the initial value theorem and say that this is equal to limit as S goes to infinity of S times IFS, which means limit as S goes to infinity of B minus AC S squared minus AD times S divided by S squared plus Cs plus D, which by the same arguments as before is the ratio of the two leading coefficients, which will be B minus AC. So this is the answer for this. So the initial value of the current is B minus AC amperes, if this is the Laplace transform or the voltage across the capacitor. Now again, to find out the value, initial value of the voltage across the inductor VL equals L di dt. In our case, the inductance value L is 1 Henry, therefore this is di upon dt, which now tells us that VL of S is S times IFS minus I0 plus. Once again, we are taking the variation of the voltage across the inductance from t equals 0 plus onwards. We are ignoring any changes from 0 minus to 0 plus values. So we again multiply the expression for the Laplace transform of it, which is this one, multiply this by S, substitute and remove from that I0 minus, which is B minus AC. If you do that, I will not go into the details of this. This will turn out to be, I will give some expression here, and then VL infinity is limit as S goes to, I am sorry, VL 0 plus, that is what we are interested in. Limit as S goes to infinity of S times VL of S. So after carrying out this work and take this limit as S goes to infinity of S times VL of S, you will get the answer minus AD minus BC plus AC squared. So that so many volts is the value of the voltage across the inductor. This example shows that once we have the Laplace transform of some quantity and to find out the initial values of different quantities associated with this capacitor voltage in this case, we really did not have to carry out the numerically the value of the capacitor voltage VCT at all, and symbolically in terms of ABCD we are able to evaluate this. So in other words, if these are particularly unwieldy numbers, say 97, 35, 9.5, whatever it is, you do not have to do the numerical work, try to find out VL of t and from that Vc of t and then try to find out I of t and then from that VL of t, and then find the initial values of these respective quantities. You can straight away use the initial value theorem and get all the initial values of the quantities which you are interested in. Let us consider one more example. Using the rule for periodic functions, find Laplace transforms of two functions A a pulse train like this, like that it goes 0, t upon 2, t, 3t upon 2, 2t, 5t upon 2, etc. with an unit amplitude. B, a single pulse of a sinusoid 0 to t upon t naught upon 2, where omega naught equals 2 pi upon t naught. So this will be, suppose this is 1, this is sin omega naught t in the interval from 0 to t naught upon 2. So I can write this as ut minus ut minus t naught upon 2. This is something which we already discussed earlier, but we would like to arrive at the result in a different fashion. Now take this. We have a pulse train here. So if we know the Laplace transform of one single pulse, we can find out the Laplace transform of the pulse train, because it's a periodic repetition of the same event. Whatever is happening from 0 to t, capital T, is repeating itself. So if you want to find the Laplace transform of just this portion, we know that this is equal to u of t minus u of t minus t upon 2. This function is simply a step function minus a delayed step function starting at small t equals t upon 2. Therefore, the Laplace transform of this is 1 over s. This is the Laplace transform of this is 1 over s. The Laplace transform of this is the same 1 over s, but multiplied by e to the power of minus t upon 2 times s. That is the Laplace transform of this. Now all we are having is the same pulse is repeating itself identically every capital T seconds. Therefore, this is a periodic phenomena, and we found out the Laplace transform of the phenomenon in one period. So the entire periodic function will be obtained by 1 over s 1 minus e to the power of minus t by 2 s, the basic function, divided by 1 minus e to the power of minus t s, according to the rule that we had earlier derived for a periodic case. So the answer is 1 over s. You can put it in this form if you wish, or 1 over s times 1 over 1 plus e to the power of minus t by 2 s, because this is a factor here. So that is the answer for this the Laplace transform of this periodic pulse train. Now when you go to B, we have derived this in a different fashion, but now I would like to derive it using the property of the periodic function. Suppose I call this g of t. Then let me say that this has a Laplace transform g of s. Now suppose I extend this like this. I complete the sine function for one complete period. If this had a Laplace transform g of s, what would be the Laplace transform of this? This portion would have the Laplace transform g of s. Suppose this portion had been flipped over like this. This had been flipped over like this. Its Laplace transform would have been g of s multiplied by e to the power of minus t naught by 2 s, because the same thing is delayed by t naught by 2 seconds. So the Laplace transform of a simple a loop like this would have been g of s times e to the power of minus t naught upon 2s, but now instead of this we are having a negative going thing. Therefore, this will be plus minus g of s times e to the power of minus t naught by 2 times s, or in other words the Laplace transform of this one period of this sine wave would have been g of s times 1 minus e to the power of minus t naught by 2 times s. That would have been that would be Laplace transform of this in terms of the Laplace transform of this. Now suppose this sinusoid is repeated endlessly. So that is a complete sin omega naught t ut repeating endlessly. Since we know the Laplace transform of one period, you can find out the Laplace transform of the entire periodic function by dividing this by one minus e to the power of minus t naught times s. This is the Laplace transform of this. But we know the Laplace transform of this. This is after all sin omega naught t ut. And we know the sin omega naught t ut has a Laplace transform omega naught over s squared plus omega naught squared. So the Laplace transform of this, which was derived in terms of the Laplace transform of the single loop, must be equal to omega naught over s squared plus omega naught squared. Therefore, equating these two, we get the result that g of s equals omega naught over s squared plus omega naught squared multiplied by 1 minus e to the power of minus t naught s divided by 1 minus e to the power of minus t naught s upon 2, which is simply omega naught over s squared plus omega naught squared into 1 plus e to the power of minus t naught s upon 2, a result which we have already derived in the last lecture or so using a different property. What we did was, if we had a sine wave like this and another sine wave which is delayed by t naught of 2 seconds, if you added these two, you would produce this pulse. So from this we arrived at the same result in a different way, but now we got the same result using the property of periodic functions. We had so far talked about the transformation in the forward direction, that is, given function of time we are trying to find out the Laplace transforms. But in the solution of network transients, we also have occasion to find out the inverse Laplace transformation. Given f of s, we should like to find out what the f of t that corresponds to it is. This is called inverse Laplace transformation. Now this inverse Laplace transformation can be approached from 2 points of view. One is to the what is called the partial fraction expansion, that is what we will discuss primarily. It also can be approached through the defining integral relation of f of t, getting f of t from f of s, the inverse transform integral relationship, which goes, as you remember, 1 over 2 pi j integral from c minus j infinity to c plus j infinity of f of s e to the power of s t ds. The second approach is little complicated and it can be used only for when special occasions arise, but for ordinary purposes it is enough we know how to find the inverse Laplace transformation to the partial fraction expansion. So let us consider the partial fraction expansion as the method of as the preferred method of finding out the inverse Laplace transformation. The approach that we take up here is somewhat analogous to what we do when we take up the integration of functions. You know, when we have to integrate something, the integrand is split up into components which are recognized to be the derivatives of some functions. So once we recognize the derivatives, then the functions whose derivatives they are we know, and then sum of all those functions will be the integral of the various derivative functions that we know. More or less the same approach we take up here also. In other words, normally the f of s that we have to deal with is a rational function. So, we split up this rational function as the sum of small elementary functions which are Laplace transforms of known time functions. So, if you do that, then the sum of all these elementary functions will have an inverse Laplace transform, which is the sum of the corresponding time functions which we recognize as the mates of the elementary functions. That is what we do. So, split up f of s, the philosophy is split up f of s as the sum of elementary terms which are Laplace transforms of known time functions. This is the philosophy. So, let me illustrate this. For the particular, let us take f of s as a rational function, which is the ratio of two polynomials in S, Ps over Qs. And we know the values of s which make the numerator 0 are called the zeros of this function, and the values of s which make the denominator 0 are called the poles of this rational function. So, let us take the case all poles simple. All poles are simple. In other words, Q of s is the product of some constant k times s minus si, where all si are distinct. That means, if you take I from 1 to n, whatever the factors here, all of them have different values. No two repeat themselves. None of these poles repeats itself. That means no two si are the same. Now, to handle this, we can write this f of s as k1 upon s minus s1 plus k2 upon s minus s2 down the line kn over s minus sn. If there are n such factors in Q of s, say I from 1 to n, then there are n such factors, and if the numerator degree is the same as the denominator degree, you also have a constant term sub k naught. We will assume in our case that the degree of P of s is not greater than the degree of Q of s, which is usually the case. So, we do not have to worry about cases where you have stop with k naught, you do not have terms like ks squared and so on. So, this is f of s. Now, if this is the partial fraction expansion of f of s, where all poles are simple. So, given P over Qs, we have to put this in this form. If you do that, then we can find out the inverse Laplace transform of each one of these elementary terms quite conveniently. So, that is our first job is to express Ps over Qs to be like this. Now, how do we find the values of k1 to kn? Now, you observe, suppose I multiply all these terms, both this side of the equation and this side of the equation by s minus s1, then I get k1 plus k2 over s minus s2 times s minus s1, etc., plus kn times s minus s1 over s minus sn plus k naught times s minus sn s1 equals Ps over. As far the denominator is concerned, because s minus s1 is the multiplying factor in the numerator, one particular term gets dropped out. So, you have some k, the product of s minus si, I starting from 2 to n only, because s minus s1 got dropped out. Now, if in this put s is equal to s1, suppose I substitute s is equal to s1 in this, then all this will vanish, and on the left hand, on this side you have only k1, and on the other side you have therefore Ps over Qs. What I have really done is we have multiplied this by s minus s1. Therefore, this s minus s1 got cancelled out in Q of s, and that left this. So, I can put this in this form, Ps times s minus s1 by Q of s with the substitution s is equal to s1. So, that is how you can evaluate K1. In general, any one of these, suppose you want to find Kr, all you have to do is Ps multiplied by s minus sr divided by Q of s. That means this s minus sr term is cancelled out in Q of s. Symbolically, we represent it in this fashion, then substitute s is equal to s. So, that is how you can find out all these factors. These are called the residues of these poles. K1 is the residue of the pole at s equal to s1, K2 is the residue of the pole at s2, Kn is the residue of the pole at sn. So, we can find out all these residues, and once we have all these residues, we can find out the corresponding f of t. So, once we have this f of s, corresponding f of t is easily obtained by finding the inverse transform of each one of these. We recall that K1 over s minus s1 as the time corresponds to the time function, which is equal to K1 e to the power of s1t. Similarly, K2 e to the power of s2t, and so on and so forth. One quick example will illustrate this, and then we will be done with that as far as this lecture is concerned. Example: suppose f of s equals 2s plus 3 over s times s plus 1 times s plus 2. So, it has got 3 poles. So, I will have K1 over s plus K2 over s plus 1 plus K3 over s plus 2. So, these are the 3 terms that we have to evaluate. To find out K1, you multiply this function by s. So, once you multiply this function by s, you have 2s plus 3 over s plus 1 times s plus 2, and substitute the value s equal 0, because the pole is at s is equal to g origin, pole at s equal to 0. This will be 3 upon 2. Now, as far as K2 is concerned, you multiply this function by s plus 1. So, 2s plus 3 over s times s plus 2, substitute s is equal to minus 1, because s plus 1 must be made equal to 0. So, s is equal to minus 1. If you substitute s is equal to minus 1 in this, you get the answer minus 1. And likewise, K3, you multiply this by s plus 2. Therefore, you have left with 2s plus 3 divided by s times s plus 1, and you substitute s is equal to minus 2. And the answer for that happens to be minus half. So, the partial fraction expansion of f of s leads to these 3 terms K1, K2, K3, which are evaluated like this. So, from this f of t can be obtained as K1 by s, 3 by 2 upon s, it corresponds to 3 by 2 ut, plus K2 upon s plus 1, this corresponds to K2 e to the power of minus t. K2 is minus 1, therefore, e to the power of minus t ut. That is the inverse Laplace transform of K2 upon s plus 1. The inverse Laplace transform of this is K3 e to the power of minus 2t. K3 is minus half. So, minus half e to the power of minus 2t ut. That is the final result, 3 upon 2 minus e to the power of minus t minus half e to the power of minus t 2t ut. So, this is how one can find out the partial fraction expansion in the case of simple poles, and from that you can find out the time function to which the original given f of s corresponds to. So, in this lecture we worked out various examples to illustrate the properties of Laplace transforms we had studied earlier, and then we started a discussion on the method of finding out the inverse Laplace transformation of a given function of s, that is to find out, identify f of t to which the given f of s corresponds. And in this direction we started out with the partial fraction expansion of the given function of time, given function of s, and as a first case we have taken the situation where all poles are distinct and simple, that means no pole is repeated, and we can find out the residues of these poles in a very compact way by multiplying Ps upon Qs, the rational function, by S minus Si, where Si is the pole at which you have to find out the residue. So once these residues are found out, all the k factors are found out, the inverse Laplace transformation is quite straightforward, and that is what we have illustrated by means of an example. We will continue this discussion of finding out the inverse Laplace transformation by partial fraction expansion in the next lecture, where we will consider the situation where some poles are repeated, maybe of order 2 or 3 as the case may be.